Alright, Chemical Bonding 5. We're going to review a little bit on the atomic emission spectra, and then we will get into these topics here. So the continuous spectrum of light, right, is wavelength increases, frequency decreases. The visual spectrum of light, which comes from white light, can be divided into all colors of the rainbow. Indigo light has a wavelength of 400 nanometers, and red light has a wavelength of 750 nanometers. So the rainbow represents a continuous spectrum. It just kind of fades into the next. An atomic light source may be attained by burning an element over a flame, like we did in the flame test, right? Or you put gases like neon gas in a glass tube, and electricity flows through the tube. It gets excited, like you saw in pre-AP. So these are known as the neon lights if they use the noble gases. Every gas produces a characteristic color, and when this light hits the prism, in different wavelengths of light that are present in the original ray are refracted at different angles. So every element produces a characteristic set of wavelengths. This is just one method of identifying elements, so you could use the atomic emission spectrum. It doesn't produce a continuous spectrum because it's not possible to produce every single color. So it has its own unique spectrum. So hydrogen will always produce this spectrum, and we can identify hydrogen using this. And every other element on the periodic table has a distinct atomic spectrum, which is different from that of all other elements. So why do we have different colors of light? So again, wavelength frequency changes, color changes. And there's a duality to light. It's a wave and a particle. So why do atoms produce light spectra? So this is the Bohr model of the atom. It contains the different principal energy levels, the shells. So for this discussion, we'll assume that all the electrons within a certain energy level contain the same amount of energy. So electrons in the n equals 1 energy level contain the least amount of energy, and energy per electron increases as we move outward to the other energy levels. So when an electron is excited by an influx of energy like a flame or electricity, it jumps up to a higher energy level and then immediately drops back down. As it drops back down to its original energy level, it emits a photon with an amount of energy that is equal to the difference in energy between the upper and lower energy levels. So as the amount of energy contained by an electron at a certain energy level is constant, the difference in energy between two energy levels is also constant. So for every photon that is released, an electron drop from n equals 5 to n equals 2 contains the same amount of energy. So according to Planck's formula, all photons with the same energy also travel with the same frequency and therefore exhibit the same amount of light. So here, we're getting energy promoted, and you get the red light coming out. Here you get the green light coming out. If it goes up to another shell, promoted to n equals 4, it drops back down, emits the violet light. If it drops back down, it'll produce the blue light. So hydrogen could emit all these spectrums. It could do the red, the green, the blue, and the purple, depending on where it's going to promote that electron to. Okay, this is a review of the hybrid orbital theory, which was covered in the last unit, right? It's very useful for explaining molecular geometry. Okay, now we're going to look at molecular orbital theory. It's a completely different theory of chemical bonding, which is used to explain different observations. So in this example, we're going to look at hydrogen, and it's going to form two hydrogen atoms. Are going to form H2. Two orbitals are formed. The sigma with the little star is anti-bonding. That means it's not involved in, if an electron's in the anti-bonding orbital, it's not involved in bonding. The electrons are spending most of their time away from the region between the nuclei. The sigma 1s, that is bonding. That's a bonding orbital. It's involved in bonding as electrons spend most of the time in the region between the nuclei. All right, this is a molecular diagram of hydrogen, H2. It describes the energy associated with the orbitals and the location of the electrons in the molecular orbitals. So the sigma 1s molecular orbital is at a lower energy than the original 1s orbitals of the two atoms. So this is where we start. We have the first hydrogen here. It contributes 1 electron. We have the second hydrogen atom here. It contributes 1 electron. And as you go up, you increase your energy. So if you notice, we've got these 2 electrons right here. They're going to bond. It's more stable. It's at a lower energy. So they're both contributing an electron. They're forming a bond. And we've run out of electrons. That's it. That's all they had to contribute. So we're not putting any in the anti-bonding orbital. So it's empty. Okay, here's the molecular orbital diagram for oxygen. So we've got 2 levels now. So we've got a sigma level down here, and we've got the pi's, because these are the valence electrons of oxygen. So electrons in O2 are contained within bonding and anti-bonding molecular orbitals. Notice that the bonding molecular orbital are always at a lower energy than the atomic orbitals that they were derived from, and the anti-bonding molecular orbitals are always at a higher energy than the atomic orbitals they were derived from. Bonding molecular orbitals cause stability within the molecule, and the anti-bonding molecular orbitals cause instability. That's why they're at a higher energy. Okay, here's one for HF. So hydrogen, this is hydrogen. This is what he's contributing to the bond. Here's fluorine and all its valence electrons. That's what it's bringing to the table. So this one will go here. This one will go here. We have some in bonding. Then we're going to bond the P's. And they're all going to come from fluorine because hydrogen's out. Here's a summary of your bonding and anti-bonding orbitals. Spectroscopy. So a method of analysis which is based upon the absorbance of electromagnetic radiation by matter. We can get data pertaining to the structure through spectroscopy. So the intensity of electromagnetic radiation striking the sample, I is for intensity. This is the one exiting the sample, and this is absorbed by the sample. So intensity increases as the amplitude of the wave increases. Intensity also increases as the number of photons increases, so the light gets brighter. In spectroscopy, though, some photons are absorbed by the molecules in the sample, so fewer are transmitted through the sample. So there's 2 ways you can, or 2 methods used for spectroscopic analysis, ultraviolet and infrared, and we're going to talk about both of them. So ultraviolet uses electronic energy levels, the transitions between, and it's used to determine concentrations of solutions, and we'll do this later when we talk about solutions. All right, so when molecular orbital theory is applied, the transitions of electrons in molecules are the same as those for atoms, which we looked at earlier. The energy associated with electron transitions, the quantized difference in energy levels, is equal to the energy contained by the photon that is able to move an electron from a lower energy orbital to a higher energy orbital. And the spectrometers give these values, which are proportional to frequencies in accordance with C equals frequency times wavelength. Okay? So the 2 peaks correspond with energy transitions within the molecular orbitals. From the graph, we can see it happens about 480 and 600. So 480-ish, 600-ish. So this tells us that the energy transitions between the 2 molecules, if we would plug them into these equations, we could find the energy. So the UV-Vis spect is only possible if the compound has pi bonds or lone pairs. So for some compounds, these transitions only occur with wavelengths of light that are less than 200 nanometers. So this method can't be used to gain data on electronic structure of such compounds. So the energy must be contained, or the energy contained by the incident photons must be exactly the same as the difference in energy between the 2 molecular orbitals in order for the photons to be absorbed and transmitted to higher energy. Colorless species can only absorb UV light between 2 and 400 nanometers in these experiments. Any colored molecule can be used in the UV vis spec experiments because they will absorb all light from the visual spectrum. All right, Beer's law. The absorbance, A, is the amount of light that is absorbed by the sample. The molar absorptivity is a constant that's specific to the atom, ion, or molecule being examined, and the wavelength of light that is being transmitted through the sample. The path length is the is the length from the front to the back of the cuvette that's placed in the spectroscope. As the path length that the light travels through increases, the absorbance will increase as the light will encounter more particles. So when concentration increases, the absorbance will increase as the light will encounter more particles. All right, so here's an example. A spectrometer with a 1 centimeter path length cuvette was used to measure the absorbance of hemoglobin at 576 nanometers. The absorbance was measured to be that. Use Beer's law to plot for the hemoglobin to find the molar absorptivity. All right, so I'm going to use Beer's law. I'm going to plug in my numbers and my absorptivity, is 1.55 times 10 to the third per mole concentration. B, find the concentration if the absorbance is 0.46. I just plug it into Beer's law, and my concentration is 3 times 10 to the negative 4. Okay, so now let's talk about infrared spectroscopy. So all covalent bonds in molecules are vibrating. Bond length is the average distance between the two nuclei, if you'll remember. Covalent bonds have a vibrational frequency that in the IR region of the electromagnetic spectrum. So the IR radiation of exactly the same frequency will be absorbed by the same molecule. Wave numbers are the reciprocal of the wavelengths measured in centimeters to the negative 1 power. IR spectra are often plotted with wave numbers along the top and wavelengths along the bottom on the x-axis. So infrared spec can be used to identify bond types, functional groups, and compounds. So here we want to use the table of IR wavelengths and wave numbers of absorption to identify the peak associated with the CO bond. So if you look at the wave numbers, the previous slide, the CO peak is between 630 and 1800. So this peak right here. Let's see. There it is, that peak right there. All right, try these problems on your own. We'll go over them in class.